From the studios at WMFE in Orlando, Florida, this is the Space Exploration Podcast asking the question, are we there yet? Thanks for listening. I'm Brendan Byrne. So if we're going to work and live on Mars, we need a place to live, right? Well, there's all sorts of plans to bring habitats with us, something like an inflatable tent. Well, that's great and all, but you need to get it there, and extra mass means extra rocket fuel. Well, what if we could build a habitat once we get there? Well, that's the question NASA asked some ambitious teams of engineers. Design a 3D printer that uses the resources already on Mars to build a habitat. Well, Keegan Kirkpatrick is the team lead at RedWorks 3D, and he's on to something. He joins me by Skype to talk about building structures on the red planet. So, Keegan Kirkpatrick, let's talk about Mars habitats. What are some of the challenges if we're going to kind of explore Mars? What do we need when we get there?
Well, it depends on how you want to set it up. Now, if we're just going from the perspective of RedWorks, the immediate challenge is how do you acquiesce and print regolith reliably for a long enough time to where not only you can build the first habitat, but the next 30 or 100 habitats and all the infrastructure required to keep people comfortable and alive on Mars for the long term. Now, one elegant little solution to that we've been looking into, and we've been very enthusiastic about, has been, rather than printing 150 habitats to make use of, 400 to 500 plus people, make use of structures that are already in the environment. Mars, as has been often said by science fiction writers and NASA engineers, has home to these big underground lava tubes, crevasses, a lot of the geology that you find on Earth, but it's a little bit larger than what you have on Earth. I think they say the lava tunnels can be hundreds of feet wide on Mars. So one of the things we've been looking into has been, rather than just build a habitat deep in regolith on the surface, use that regolith to print a habitat that could effectively seal off a cave or crevasse or open pit mine or whatever, pressurize that chamber, and you essentially micro-terraform one little section of Mars that can grow organically into a community.
Interesting. Now, I want to go back to something you said. You said to print a habitat. What do you mean by printing these structures?
Well, printing is very much it's an umbrella term these days, but the technical term is extrude. For our purposes, it involves melting regolith, which is Martian dust. Well, dust is a generous term. Calling Martian dust would be like if we called dust here on Earth gravel. It's fines that are only a few microns wide. Very, very difficult stuff to work with if you're trying to seal yourself off. We've only recently kind of solved that problem with what we've seen on the Mars rovers that have been going around on for the last 7 years with these neat little innovations in labyrinth gears. I'm getting ahead of myself, though. What we do is we take that dust, we collect it, excavate it, however it needs to be gathered, and then it goes through a crucible heating element, converts it into a molten substance that has the consistency of about taffy almost, and then it is laid down layer by layer like you would if you were doing a traditional ABS 3D printer here on Earth, and it hardens to about the strength of gypsum concrete.
And so that's how you build up your structure there. So you're taking what you have there on the Martian surface, melting it down, and using that as your substance to build.
Absolutely. And this is not... the technology behind this is really not that difficult to get your head around. The basics of it have been around. The most complicated stuff is maybe 10 years old. The simpler stuff on it has been around, is basic engineering principles that have been around for centuries.
And so we're talking about kind of like a desktop 3D printer you have, just at a much larger, massive scale, right?
Close, but there's one major difference. What we're trying to build is something that can move around and not just be confined to wherever it happens to land upon. We need to build an adaptive system that can service whatever needs a future colony will actually have. It can't just be something that sits up, builds one habitat for one predetermined size. It has to be able to adapt to whatever the needs of the colonists end up being. And then after it's done doing that, be something that can be reused for constructing roads and fuel supply lines and microfactories and all the basic infrastructure that a new society on a new world will ultimately need.
What are some of the physical challenges to making a piece of equipment like this? Do you have to build it all here on Earth and send it there, or does it have to be built in parts? How's the process going?
Well, if you're building a robotic system that's going to be going to Mars, you've got a couple of options. One is to make it a very modular system. The advantage of that is that you would essentially build one leg, one extruder head, and break it down into the most compact little array of parts that you can possibly stick on one package and send it off to save volume. But mass-wise, which is the real cost of getting anything into space, you're not making much of a savings there. But the advantage to the system to begin with is that you're already saving virtually, you could almost say you're saving infinite mass, because you're sending as many habitats as you need with the crew from day one. They can build it all there. They're not having to send a titanium tin can to Mars every time they need to expand anything that's a critical system or replace anything that gets damaged. So the advantage of building like a modular system is that if one component is damaged in any way, you can remove it, lop it off, wait for the next mission to bring a replacement component, reduce mass that way. But most of it would have to be built on site on Earth. Now, we are looking into techniques to where you could, it's the Holy Grail theory, the best printer is one that can print a copy of itself. We're looking into ways how you might be able to pull that off, but we think that's a little bit further down the road.
What particular challenges do you face using this technology on Mars itself?
The biggest challenge, the two biggest challenges we can see are how do you keep it operating long-term when exposed to the elements on the surface of Mars, and radiation and low atmosphere is not as big of a challenge as it sounds. It's mostly fines. You have to make the thing almost more than airtight to be able to seal itself off from this. There's a report, there's an old story, Gene Cernan, last astronaut on the surface of the moon, once said, if we had the oxygen and the water to stay out here for an extra couple of hours, it wouldn't have mattered. The suits were already absolutely shot just from what lunar finds, which are very similar to ones on Mars, were doing to just the bearings and the seals that the suit itself had. So we have to protect against that. Now, fortunately, NASA and a lot of other engineering teams have made a lot of headway with this, with what are called labyrinth gears. I won't get into too much of the details on the mechanical engineering of this, but these are the basic technology that has let a little rover like Opportunity operate for 7 years, exposed to every flavor of weather that Mars could throw at it. And we got to look into adapting that to our systems.
How do those work?
They're like a multi-seal kind of a thing. I don't want to get too deep into it just now. But they basically let you have something that can move continuously, but at the same time seal any of the internal mechanisms off from its environment. Gotcha. Now, the second biggest challenge, on top of being able to make this something that can last long-term, is how do we make sure that the biology systems that we're sending to this world, because we're not just talking about sending a self-contained system with a bunch of MREs. We're talking about creating living systems inside these habitats that can provide air, food, and clean water. How do we tailor that to be something that is long-term and scalable for whatever type of habitat needs to be constructed? Now, again, there has been a lot of work done on this already, so right now for us, it's just optimizing everything. And we're going to be looking into doing a little bit of front-end tests of our own very soon. Can't get into any more detail beyond that for those just yet. So those are the two biggest challenges that come to my mind immediately.
This is long-term, establishing a permanent presence on Mars here. What are some of the things that your machines are going to need to build so that we can actually stay there for a long period of time and colonize?
Well, the immediate thing is to be able to build the habitats. Now, the habitats that we've designed, and people can look at some of the front-end ones we've released online at redworks3d.com, shameless plug, are designed to be fairly self-contained systems that can support 4 or more, or potentially less, because they are supposed to be extremely scalable, astronauts for at least a year, with all necessary biology-driven life support systems on board. Now, that's just to keep one crew alive for expeditionary and exploration missions before they seal off, a cavern or whatever they have available to them and expand from there. What they are also going to need is the infrastructure required to operate on the surface and build the equipment to maintain any payload deliveries from Earth. And this is hardware that can't be readily reproduced on the surface of Mars with 3D printers. I don't see us making silicon wafers on Mars for a few years, at least. And I think I'm being generous there. So this means building the refueling stations, the fuel lines, the electrolysis factories to be able to split water ice or synthesize methane, which I believe is what SpaceX is looking into using as their main fuel source. looking into what they'll need to do to be able to convert Martian soil, not soil, it's Martian regolith, into actual soil. How do we create self-contained factories that can basically be little biocookers that can convert Martian regolith, which is a combination of perchlorate salts, silicates, and iron, a little bit, which is iron oxide, and convert that into all the lovely little things that we take for granted that is in the dirt of Earth, and use that beyond the initial aquaponic systems that we want to set up for our life support systems on these HABs, and use it to be able to create long-term biomass in an expanded colony. So that's kind of a short list of the things that immediately come to my mind for what has to be built on Mars for long-term survivability.
I'm interested in talking about the idea that you've mentioned about kind of using those natural features of Mars, using those lava tunnels, going under the surface. How would you go about doing that and making that a livable habitat? And is that more of a long-term thing than say printing something that's on the surface?
That is absolutely a long-term project, one that we are still looking at from a preliminary perspective. Now, the way that we could do it is we've got a couple of options. One is to terraform mechanically, which is creating a lot of chemical processors and whatnot that you would have to either bring with you or build on the surface. Probably, given the complexities involved, you'd have to bring it with you. The simpler option, that is more practical than I think a lot of us like to think about, is being able to do it with biological systems. This is using genetically engineered bacteria to convert perchlorate salts into biostructures in the soil, or to amass water and hydrological systems that are in the Martian regolith and convert a more hardy soil base. Using biosystems that are on board the habitat that are not necessarily genetically engineered to filter through CO2 and pump up the atmosphere into this expanded cavern. Use processed waste from the astronauts themselves to continue to build up that good soil base, and to give the basic elements you need to generate a breathable atmosphere and the basic infrastructure you need to grow large quantities of food to support a fairly large population.
How big are these caverns, Keegan?
Well, we don't have a whole lot of information on the surface scans. I've seen some reports that have talked about them being miles and miles long and several hundred feet wide. Was a study recently, I can't remember the report for the life of me, that estimated the ones on the moon could be upwards of 6 kilometers in diameter. You could drop Philadelphia inside one of those things.
So we're talking, these could possibly be large underground cities on the surface of Mars.
Think farming town for the start of it. I kind of have this almost Miyazaki-esque image in my head of rolling green hills with moss-covered caverns heading up to the apex, where you see this tower heading up, bringing you up to the surface of this dead world from within inside a new living one that you've created on the surface.
It's like from the pages of science fiction is what it sounds like you're talking about now.
Science fiction is only fiction before time has passed to allow it to become fact.
You're kind of laying out the groundwork for this idea of bringing this machine that can take the natural resources, build these semi-temporary structures that will lead us into building these permanent structures using the natural geology of the planet. How can you take this plan and kind of bring it to other planetary surfaces or whatnot?
Well, I'm glad you brought that up. Now, Mars is the long-term goal, but where the industry is heading right now is often called the pivot to cislunar. Cislunar is the new umbrella term for, geostationary orbit, near-Earth asteroids, around and on the surface of the moon. And this is where we have to start talking about how national interest relates to space. Now, right now, we are at a point to where space is no longer just something that is convenient or useful to the global economy. It is a vital thing that the entire global economy depends on. And that means that we now have to start looking into securing space assets, not just from, space debris is one of the favorite ones to throw around, and yes, that is important, but we're talking about solar flares or potential incidents where hostile powers might disable or sabotage structures in space. How do we secure those assets that are vital to the global economy? And one of the things that's going into that is in-space servicing. And one of the things that is going to service that is satellite refueling, repair, and maintenance. And to have a relatively large quantity of fuel on hand to operate in space, you pretty much are stuck having to pull ice off of asteroids, split it out into hydrogen and oxygen, and use that as your fuel source. And what we are looking into is to provide the initial layer of infrastructure to operate on asteroids and the moon, to provide those resources to maintain our current satellite networks and expand them, which is expected to happen in a big way. The Air Force recently gave a public talk talking about how it would not be unreasonable to suggest that 1,000 launches could occur in the next decade or so. That's, if I recall correctly, double the current number of active satellites the U.S. has in orbit. Now, that's just from the private sector. The current big boom that is happening right now is in Earth imaging technologies, which is kind of tied into where big data is coming from. If you have access to satellite systems that can count the number of cars in Walmart's parking lot, you can then have usable data to figure out how to optimize not just better parking lots, but how consumers move into a store. And that leads back to how the economics of an entire retail chain works. And that leads to how the regional economics, it's this huge new boom that is driving a massive new interest in space and a massive new interest in how we deal and maintain our space networks.
Great. And so that's going to kind of be the driving force behind this technology to make what you need when you get there.
Absolutely. That will be where REDWRX habitats are first going to be used, is to make this, lay the groundwork for the expanded use of activities in cislunar space. Now, the big flagship project that NASA has been pushing in recent years, year singular, is the Deep Space Habitat, which is this new, it's being called a space station, but to my mind it's a ship, a real ship, that's going to be put in cislunar space beyond geostationary orbit, that Lockheed's been talking about using it to be able to deliver payloads and crews to the surface of the moon. It'd be a space tug. So the money is now being spent. The interest is there, and more importantly in all, the United States, the Russians, the Chinese, the big players in space are all seeing that cislunar activities are going to be something that their countries have a vested interest in protecting and expanding for the long-term economic health and welfare of their countries.
It doesn't hurt that there's valuable minerals on those asteroids and in the moon, right?
That's long-term. The first real money that will be made in space will be from getting access to liquid water that can be used to not just supply crews, but provide long-term fueling and servicing of expanded satellite networks. Now, eventually, yes, the platinum group and even simpler metals in space are going to come in handy in a big way. There's always the talk of helium shortages or how we might be running out of copper, but the near-term stuff will probably be rare earths, platinum groups like rubidium, tungsten is another big one that I hear kicked around every so often. That's where it's going to grow long-term.
Keegan, how soon do you think it will be until something from your shop is launched to a distant planet or an asteroid and is in working order? Realistically, when is the market ready for something like that?
Oh, this is always such an unfair question to ask an engineer because we get way too excited about these things. It's remember, I've lived through 4 or 5, depending on who you ask, programs where NASA, the Air Force, whoever was swearing up and down, we'd have brand new super heavy lift or single stage to orbit launch vehicle in the next 3 to 5 years, and then it ends up going nowhere because there was a technical problem or money dried up. And being in the private sector, we don't have to play by those rules necessarily, but still, engineers have a bad habit of overestimating how long they can realistically get something done. If I'm coming at it honestly, I would say 3 to 5 years to put something practical and usable that can have near-term economic benefits on the surface of an asteroid is a reasonable time scale. In my gut, I say I could do it in 2. But again, don't trust the engineer on time scales when he's really excited about something.
So 3 to 5, that's soon. That could happen. That's not very long term when you think of other space programs and equipment like this.
Well, you have to remember that we are not constrained to the launch problem. When you're not the guys who have to actually put the hardware up there, you're just, in a sense, a subcontractor of sorts. You're providing other organizations the resources they need to operate in space. Your cost of doing business falls substantially.
What are you most excited about, let's say, in the next 5 years when it comes to this technology?
That's a really unfair question, man. Come on. Next 5 years? Oh, boy. Well, let's see here. 2021 timescales. If I was really pressed, I would have to say it's a tie between advanced hypersonic single-stage orbit systems and probably lunar and asteroid mining operations. That's probably the big two. But if I had to say what is really the interesting thing is that right now we are seeing movement in space at a rate that, at least in my lifetime, I can't think of anything that even comes close. And I make a point of talking to friends of mine who've been in this business a little longer than I have, and they say, like, this is like the most amount of activity they've seen in the space industry since the shuttle program got started in the late 70s. So the real question is, what's around the corner that we can't see yet? And how is that going to completely blow the doors off of everything that we think is normal in this industry right now? And that's what I'm most excited for, is that we're living in an era in where the unknown is coming back into space flight. That's the fun stuff.
Keegan Kirkpatrick, he is the team lead at Redworks 3D. Keegan, thank you so much for talking with me.
Yeah, Brendan, been a lot of fun.
That's it for this episode. Support for Are We There Yet comes from the listeners of WMFE. You can follow the show online. We're at Twitter, at AWTYMars, or reach out to me in the Twitterverse. I'm at Space Brendan. Leave us a review if you listen on iTunes. That's how more people learn about the podcast. Are We There Yet is a production of WMFE. Our theme music was composed by Kevin McLeod. Production assistance from Adam Mano. Find more space news online at WMFE.org/space. I'm Brendan Byrne. Thanks for listening.